Have you ever heard of Rheo Casting? And do you think you can do that at home? I did. Not the best one, but as the rule said, I had to stir it to be able to make it flow because it is a texture molding process. Texture means that it changes viscosity when you stir in it. But will this be the big new in the future? Will you be able to make gigacasting using this technology? My guess says we might, and he also says we might be able to reduce the size of the machines with 40% or make the products 40% bigger. So if you want to see what this is, follow this episode and learn how we today can produce castings up to 70 kilos of aluminium alloys. See you. Hi, Fabian. Welcome to the podcast, Everyday Metallurgy.
Thank you for the invitation, Peter. Great to be here.
Fabian, we are colleagues in the podcasting universe. You are doing your own podcast on aluminium casting or magnesium casting. You call it gold casting because there's a lot of gold to be digged in that area. And I have invited you to join me on my podcast today because I have seen some of your episodes and I have got requests from several of my followers to dig into what is called Rheo Casting or Gigacasting, some of these new buzzwords that are out there. And then I invited you to join. So that is the theme today. But first, I would love if you could give an introduction to yourself and feel free to tell a little about your own podcast because the more people they follow, the more they learn.
Absolutely. It's always a great thing to discuss so many things with casting and then podcasting, gigacasting, Rheo casting. Perfect. So first of all, a bit about me. I'm Fabian. I'm a material engineer by training, and also I started my career by developing foundry alloys. Doesn't matter for high temperature application, sand casting alloys, or high pressure die casting alloys with aluminium iron eutectics. So something off the normal charts. And then worked a while on that. And then as soon as the more I developed the alloys, I want to have them also see how they go into real production. So I switched the company towards a company that does the actual casting, worked there a while, start doing everything from pushing the buttons on the machine to get the properties out that we promised earlier in the sales process, to get new plants set up and started. And one of the things I came across at that company was Rheo Casting, which was one of my projects. And since then, I thought, hey, that is so cool. We've seen high pressure die casting, many things. Got to the limit of what a process can do, got more and more complex, the market got tighter, margins lower. And Rheo casting was, for me, that thing that really solves most of the problems the industry has. And then I said, okay, I have to do that by myself, promote that. And yeah, that's what I do with my company, Casting Campus. And it started that way, that I was doing for several companies their Rheo casting parts, getting them from idea into series production. But then when the first wave went through, so hey, now we need a second wave, and it didn't come. And then I thought, oh, we need to start way earlier with the marketing. And so Casting Campus developed also in that marketing sphere. And then the podcast came along, and now it's basically these two pillars, Rheo casting and digital communication, that makes what I do every day.
Perfect. Fabian, I made a podcast episode with Ingolf Schruff, an expert in tool steel and hot work tool steel some months ago. And we ended that episode talking about high pressure die casting. And he told about some of the damages that could occur to the tool steel in these processes. And I couldn't get it out of my head, all these damages. And I thought, is Rheo casting the solution to avoid all those damages. So can you give a flight into what is Rheo casting and how does it differ from traditional casting?
Absolutely. So let's start with getting the obvious thing out of the way. Rheo casting is not magic, so it cannot do everything. It can do a lot of things very well, but it doesn't fix the whole world. So what it does is when you're doing conventional casting, everything is liquid. So you're getting the liquid metal inside the mold. It doesn't matter if it's a sand mold or a high pressure die casting, the plunger pushes it in the tool cavity, and then it solidifies where it ends up. And Rheo casting flips that script a bit, that you're producing, before you pour in the shot sleeve, a semi-solid slurry. So that's solid particles suspended in a liquid. And by mixing that, it gets a new kind of properties that we know more from the plastic injection molding, because suddenly that totally normal acting aluminum alloy becomes like a thixotropic material. So that means the flow behavior is completely different. And the key thing is that when you apply shear forces to a slurry, which basically looks like cottage cheese, when you just pour it on a slate.
Yeah.
But when you start applying shear forces, which when you have a narrow cavity and a strong plunger behind it, that's a perfect shear force generator, then it suddenly flows like milk. And that is what the thixotropic properties are. You can compare it, for example, these glass ketchup bottles. You freshly open them up and shake it out, the ketchup doesn't come out. And it suddenly starts to flow. And ketchup is also thixotropic.
The slurry change viscosity when you pressurize it or when it flows.
When it flows.
Yeah. Are there other materials that are similar to that?
Yeah, plastic injection molding that works in a similar way. That you have when you have these plastic and you plastify them, and their casting machines, you do it the same way. They're also thixotropic. And just because you get them shear forces in them, you get them moving, they move. And that is suddenly something where it's starting to act a bit different. And when you're talking about the tool steel damages, when you see that liquid high pressure die casting, when it hits the tool, especially for large castings, you're somewhere in the range of 650 to 700 degrees metal temperature.
Yeah.
A slurry for the same alloy is somewhere around 610 to 615 degrees. So you have a lower temperature right away. The next thing is that because you have a certain amount of solid material already within the melt, and then you see, usually I'm recommending around 35 to 45% of solid fraction, because then you can still pour it, and you're getting in a casting timeline a laminar fill. I think that's the key where we come back later. And when you have around that 35, 45% solid fraction, there are globular particles within that slurry. When you add the surface area of these in comparison to the tool steel surface, the area of the globalites is way, way bigger. So most of the solidification is happening on top of these globalites. And then the latent heat goes back into the remaining melt, and then it's like casting a pocket warmer. Therefore, you can go to immensely long flow lengths. So I was seeing one result from a trial. They went to 4.5 meters of flow length in a 3 millimeter wall thickness tool.
Yeah, that's crazy. But the alloy, so you need a solidus and a liquidus. And I imagine that you need quite a big distance between these to have that gap of slurry. So you cannot do it with everything, or is that wrong?
That's correct. So there are processes. So Rheo casting is a very wide field. It started in the early 1970s. And last time I checked, I found 87 different patents on how to make that slurry from 3% solid fraction up to 60, 70% solid fraction. And nothing really worked for serious production, because the key thing is in how to make that slurry. Before we answer your question, is that
Yeah.
Most of the process, okay, we have a liquid melt here at a temperature, we cool it down to a certain temperature, and then we have the perfect condition. However, we are not in the equilibrium phase because in the phase diagram you can pinpoint exactly where 35% solid fraction is. We are not in an equilibrium, so the slurry doesn't behave at that temperature. It has a different temperature.
There's some supercooling.
Exactly, supercooling, undercooling in that case, and that's key. So that's the first thing. And when you do that, if you have a laboratory and doing your whole tenureship as a professor with one batch of alloys, you don't see that effect. But if you have a running foundry and plus minus 0.5% of silicon content is a very tight spectrum for a melt shop.
Yeah.
Then you suddenly see that the change in liquidus temperature is bigger than the change between 20% solid fraction, which is basically a turbulent fill and a lot of blisters, and that's a scrap part, and 40% solid fraction, which is then a part that has a perfect condition. And what do you guess the temperature is?
The same.
The same is good. It's 0.8 degrees, what I measured.
Yeah. Yeah.
And imagine you want to have, when you talk about gigacasting, 60 kilos of melt within a tenth of a degree. That's also changing because the chemical composition is changing. That is impossible.
Yeah.
And that is why a lot of Rheo casting projects failed in the past. There's something new came out called the Rheo metal process, and it adds a step in between, not just cool it down. It produces an enthalpy exchange mass. You can see it. It's basically an aluminum ice cube. It's made from the same melt in the process, completely solidified, and afterwards you steer it into the rest of the melt. And while it melts off, you steer it around, you implement the shear forces, and because it's the same melt, you don't have the temperature dependency. It's just an enthalpy correlation. How much of material do I want to solidify, want to melt, and how much do I want to cool down? And then you always get the same condition, different temperatures, but the same condition every time, and that is key for the casting process.
But looking into the alloy systems, are there no-goes? I could imagine you just mentioned slightly different in silicon makes an incredible big change. So are there alloy systems that are just perfect for Rheo casting and other alloy systems that are absolutely impossible to Rheo cast?
The key thing is that you get enough primary alpha phase that you're not solidifying the eutectic system. So hypershot die casting used to have an ALSC 10 MNMG. That is the go-to alloy, but that doesn't work at all in Rheo casting. Too much eutectic phase, too narrow solidification interval. So you need, when you're talking about a pure aluminum silicon, bit of manganese, bit of magnesium alloy system, you're between 2.5% silicon to 7.5% silicon. There's some exceptions. If you have a lot of copper in them, you can go up to 8.5% silicon, but then that's the hard cutoff, and then you start again with over eutectic alloys at 14-15% silicon, for example, as the major casting. But you can also use other eutectic systems. The key is that you have a large enough solidification interval and can have around 35% pre-solidified material.
Yeah, and if we jump back to the description Ingolf gave on these failure modes, then there's not wear on the surface of the tool. I think he also mentioned the diesel effect when the gas has to come out somewhere, and then you also mentioned blisters. Due to stirring, or is it due to entrapped gas in the melt?
So when we're talking about the tool steel and the defects there, so of course there are porosity that forms because the metal encloses that air, but there are other effects that you have it because you have some water remaining in the tool and things like that. So there are different ways, and you also have the shrinkage porosity that can sometimes look similarly, but has a different origin. So venting and air is a big thing in Rheo casting, as when you have the liquid melt in a turbulent fill. It just takes every air molecule that is there and just encloses it in the melt and pushes it somewhere. Hopefully it's an overflow system. As soon as you start welding, you usually see it. However, you can also engineer high pressure die casting parts that are okay to weld. But with Rheo casting, you have that slurry front going through the whole casting. And when it goes through, it pushes everything in front of it. Therefore, when you have a right vacuum and venting concept within your tool, you get a perfect casting, no air porosity within. And then, for example, we did some castings for CO2 compressor housings. They are operating at 180 bar CO2 pressure, no impregnation, out of the box. In Rheo casting, they are leak tight.
And I could also imagine when you go to high temperature filling, your solidification shrinkage is a lot higher than when you go in a slurry. So in normal pressure die casting, you have is it called after filler? So you have to push more in when it solidifies to avoid or to compensate for the shrinkage. How is it with Rheo casting?
It's in a similar effect. So when you're taking normal aluminum alloys, you're around 6.6% of volume deficit that you have to feed in the third phase. And when Rheo casting, when you take out around 40% of pre-solidified material, you just have half of that, but you still have 3.3% somewhere around that you have to fill, and that's the same process that you need still some pressure.
And what else do you have for failure modes that you can avoid with the Rheo casting?
There are quite many things that you can do. The one thing that you should never do is just, as it's produced on a high pressure die casting machine, and it's just a different melt preparation, but taking your existing high pressure die casting tool and do Rheo casting on that is a guaranteed failure, because the whole system is not designed for that. So when we have in high pressure die casting, we have usually the gates opening up, having very short paths throughout the casting and dividing with multiple gates. In Rheo casting, you want to have one gate and then the slurry spreading out the rest. So when you would take a high pressure die casting tool, you would produce a lot of slurry fronts that have oxide layer on oxide, and that you want to have in the casting.
So you're creating these welding zones where it runs and meet.
Exactly.
Like you do in traditional casting. And are you able to see the welding zone due to oxide film created on the front, and then when they meet, you have a layer of oxide?
Yeah, they're impossible to see. You don't see it with the naked eye and X-ray. The only way to find it is with a tensile test, because then it's very easy. But you see it very clearly. You see it clearly within the simulation phase. So long before you cut the first tool steel, you already know how to do it, and you can set up your overflows that you really get that good filling behavior. But it has to be done prior. Another thing that is critical is the gating, because high pressure die casting wants to have a very thin and narrow gate to spray the metal in, to really strengthen the turbulent filling effect. In Rheo casting, that's the worst thing you can do, because then you have something called a sponge effect, that slurry is just squeezed out like a sponge. The liquid goes into the tool, the solid particles stay behind.
It stays back.
And then with the plunger, the third phase just pushes the rest in, so you get a terrible casting throughout the whole thing.
So a kind of mechanical segregation. Of the melt.
Exactly, that's something what's happened if you don't modify your gating and overflow system.
So what is the speed that you are pushing it in with?
With high pressure die casting, you're between somewhere around 40 to 80 meters per second metal speeds at the gate. In Rheo casting, that depends a bit on the wall thickness. You're somewhere in the range of 3 to 15 meters per second metal speed. So significantly lower.
But the pressure you need to push it in, I could imagine it's a lot higher in Rheo casting than it is in die casting.
That's a common misconception, because when you see something sitting there like a cottage cheese, you can imagine, okay, they need more pressure, but
Yeah.
it actually flows very well. So we usually can reduce the machine size by 30-40% because we don't need that much locking force.
That was a new way of thinking. But then if I jump to something I have seen out there in the real world, this Gigacasting, they are also done with Rheo casting technology, isn't it?
At the moment, not yet, but I
Okay.
hope we can talk about that in a few years then and seeing the
Yeah,
differences. But yeah,
yeah.
we are currently developing our way to that
Mm-hmm.
with larger and larger castings, but we're
Yeah.
not quite at the gigacasting level yet.
Okay.
However, they are the ones that profit the most from semi-solid casting.
Yeah, I could imagine because going so big and the presses they do it in are enormous. So that was also why I thought that the size and the power you need must be higher. But I could imagine if you could reduce the size of the press itself with 40%, then gigacasting, if you stay with the same size, it could be teracasting if that word exists.
Somewhere range that could be done, but usually then you end up in the situation that when you can have a smaller machine, usually the part doesn't fit when you go to the full extent, that it doesn't fit on the machine table, that you need a bigger machine. And the second thing is that the shot end cannot handle large enough plungers that you really get the metal in. So usually you have to find that compromise and then. But for these large casting, even once machine size step down, because they have an exponential curve in the cost. Because it's not just that the machine gets bigger, you need way more heating, cooling equipment. You need the larger cranes, larger tools. So going from one machine size to the next, so from 6,000 to 8,000 ton, that can be more like a doubling of the investment cost.
Okay.
Just because all the surrounding. And a 6,000 ton is already more than double a 4,400 ton machine.
Yeah. Fabian, I need to jump back to the casting principle because you said this about the temperature stays hot because the solidification energy is released to keep the temperature stable. But how is the thermal management in general in the tool when you do that? Do you control the temperature? Do you cool it with enforced cooling? Are there any differences in rail casting and high pressure die casting?
That depends a bit where you're coming from. So when you have especially a lot of casters that have small machines and they're just putting the metal in, properties are just not plastic. Then there is a big step up because you need to have tempered shot sleeve, a tempered tool, hotspot cooling, ideally micro spraying. So that means that you don't spray any water with your release agent, just a release agent. But whoever does structural castings already today has everything of that already in place. So there is no need to change anything because that is perfectly what you want to have.
So the speed of rail casting is not higher than traditional casting. You can make the same number of parts per minute as you do with the traditional way.
Usually the cycle time is always a discussion point. It depends what you currently have. For the gigacasting, it will have zero effect. For many smaller parts, they usually run on a shorter cycle time than the slurry making can come up with. But what we're usually doing is going from a one cavity tool design to a two cavity tool design. So you have a lower cycle time per part, not for the machine, but for per part. Because you can reduce the machine size or stay with the same machine, but do two castings or four casting instead of the other one.
Yeah, okay. Then if we jump into the alloy systems, are there also special alloys developed specifically for Rheo casting, or has there been the same world as in traditional casting? And how far away can you go from aluminium-based? Can you also go magnesium-based materials when making Rheo casting?
So I start with the magnesium thing. So
Yeah.
technically, you can do magnesium in Rheo casting, as it works perfectly well with Tixo molding. The only problem is that you have liquid magnesium on an open air, and that is a bit of a fire hazard. That's why I would not do that, even though it's technically possible.
Mm-hmm.
And when we're talking about the alloys, typically going back to the aluminum silicon system, because if you have 2% silicon and below, that was usually the wrought alloys in that spectrum. Then you have the casting alloys starting from LSE 7 to LSE 15.
Yeah.
And there's a white space in between. And exactly in that white space is where Rheo casting lives. We already have done a few alloy developments, for example, for 5G antennas. When they went in the mobile sector from 4G to 5G, suddenly they had 10 times the energy throughput. And now they got on the limit what the thermal conductivity of the aluminium can do to get the heat from the electronics into the cooling system. So they needed something with a higher thermal conductivity, and we developed a Rheo casting alloy called Rheo Cool. It's an ALSE 2.5, around 0.6% iron, and a lot of impurities because it's 100% post-consumer scrap. And then you can cast that into Rheo casting. Works perfectly fine.
Yeah.
And then you get a heat sink with a thermal conductivity of 185 to 195 watts per meter Kelvin. That's around 85% of what pure aluminium can do, but in a casting.
Yeah, that's pretty good. What else properties can you do? Because I could imagine that when cooling pattern is different, you also end up with different grain sizes in your final structure, and smaller grain sizes typically leads to higher strength compared to large grain sizes. So can you also make the properties better when Rheo casting compared to traditional casting?
So in high-pressure die casting and Rheo casting, the properties are usually alloy defined. Also with Rheo producing our pre-solidified material, and with that we're already setting up the grain size, because then it will just grow. So usually we have a little bit bigger grain size, but the whole patch relation is not the only thing that there is. Because usually in casting, the strength 100% material given. And the elongation, that is something where you see the casting quality. And there we see an effect that we get more elongation in Rheo casting with the same alloy, because we have less defects in our materials.
Yeah.
And another thing you can do, for example, if you want to have a certain type of properties, and especially relevant for gigacasting, when you're talking about you have 200, 250 kilograms of aluminium in your EV, but you can only use it for primary aluminium. That is not the sustainability message you will be sending. So you need to have low carbon footprint recycled aluminium in there. But if you're already at the limit of what the primaries can do, there's no chance you can add more impurities to reduce your elongation. But with Rheo casting, we can take out silicon, reduce the eutectic phase, and fill that up with impurities from secondary alloys and still get the great elongation, but with 100% post-consumer scrap alloy. And these are things where Rheo casting can really outperform high-pressure die casting, because it has that flexibility and the castability is not tied to the silicon content or the closeness to a eutectic system.
Yeah. I made a trial myself. I have bought a small melting furnace, and I played with it yesterday just to check if I could melt soda cans. And in fact, I was not really in control with temperature, So when I wanted to pour it, nothing came out. Then I could take the ladle and just shake it, and it became more liquid, and then I could pour it. So I think I have done Rheo casting myself in my garage.
You at least got a slurry out of that.
Yeah.
But you've seen, especially with that effect, that if you don't apply a shear force, that's pretty useless to use, for example, for gravity die casting or something like that, because it doesn't flow at all.
No.
But as soon as you put shear forces to it, it really flows like liquid
Yeah.
aluminum.
Yeah, it did.
And then you can also see it from what you can cast. So we did for 3G filters a wall 0.4 millimeter thick. And on the other side of the spectrum, we did casting with 86 millimeters of wall thickness with the same process.
Wow. Yeah, that's crazy. Yeah, because typically you have the rule of thumb that wall thickness in your components should be homogeneous. You cannot have thin sections and thick sections in the same. Is that also the case?
Yeah, it's not quite relevant for casting. It's more in plastic injection molding because it shrinks and it gets these strange figures. But in casting, you actually want to have a bit of a differentiation because you're living with a directed solidification path. And then you can really feed it, because if everything solidifies at the same time, you have guaranteed porosity at the end of the filling. That's why you want to have that first solidify first, and then going towards the ingot that you can feed it with the plunger.
Yeah.
And Rheo casting gives you there more possibility, and you can also feed like thick bosses at the end of the filling. We have a test tool which is 2.2 meters. We cast it on a 600-ton machine. So for relation, a Gigacasting usually has 2.2 meter. But that is on a 6,000-ton machine, and we did that trial casting on a 600-ton with Rheo casting. But it's just a snake tool. And there was at the end a boss that was porosity filled through a 3 millimeter long path.
Yeah. Fabian, the podcast is called Everyday Metallurgy because I would like to touch upon some of the things we can see on our everyday life. So if we start from the top end, the Gigacasting, there's a lot of talking about it, but where is it used? Where can I find it if I walk in the street or go to my kitchen?
Yeah, so the Gigacasting is used for most famously in the Tesla Model Y. But Rheo casting is not that shiny piece. It's more like one of the hidden champions. You see it in more and more upcoming climate systems where you use CO2 as a more efficient refrigerant. You see it in 5G antennas. You use it, but you don't see it because they're up on the mast and powder coated.
Yeah.
We've seen it, for example, in delivery vans where they reinforce the door. We've seen it in structural castings. We've seen it, and the backside of the Starlink antenna is Rheo casting to get the heat out. So there are more and more applications coming.
And do you have a number of the percentage? How big a volume percentage is Rheo casting compared to pressure die casting today?
I think that number is so small at the moment that it really doesn't matter. It's a few zeros. So it's really at the moment still a niche process. But when you want to go beyond what high pressure die casting can do, because Rheo casting will not replace high pressure die casting. High pressure die casting is a perfectly good process for so many parts. But when you want to go beyond what high pressure die casting can do, then Rheo casting is the perfect process to add.
Yeah. And if I look to today, it's so small, but how do you see the outlook? If we look 5-10 years ahead, what kind of applications will show up, and what volumes do you think they will take?
I can imagine that I am a bit biased in that answer, but I will see that Rheo casting is the perfect addition for every foundry, because the biggest problem at the moment is not cycle time, energy, efficiency, and things like that. The biggest problem is that for most foundries, around 30 to 50% of the capacity is empty. New projects are purchased so cheap that they are below their cost basis. So finding new markets is the key thing for the foundry industry, and we see currently that a lot of companies that are not good in that or have projects that run out and don't get another one, they are facing bankruptcy left and right. So it's quite a difficult time at the moment, and Rheo Casting is way better in getting good properties. It's way better in developing new markets, getting new properties that no one else can do. For example, you can go into your friends from the sand casting, take a look at their casting. Same alloy, take the parts that are in high volume, put them on this high-pressure die casting machine with Rheo Casting. You get the same properties with a way better efficiency as a cheaper cost, and you get a higher margin. And you can develop things. So we talked with a company that does something around the house, and they said, yeah, we try to get to several foundries to help us, but they also were focused on automotive. Now we do a lot of weld construction, and now they are at also limited. We need thermal conductivity. We need large aluminium parts that are leak tight. Perfect applications for Rheo Casting, and now they are starting up. So a lot of the success of the foundry industry and the success of Rheo Casting depends on how good as an industry we can develop new markets.
Yeah, so you can use it to make pressurized system.
For example, would be a perfect opportunity because you don't need an impregnation step in between. You can have awesome welding results. So as we see with the CO2 compressors, that is basically taking away parts from forging because they don't need a high strength you get from forging. They just need the leak tightness, and we can replicate that in Rheo Casting.
Yeah, and the reason why weldability was so easy or so much better was that because you avoided the mix in of air during the injection.
Yes.
So that alone can create a bad welding.
Yeah, that really makes it easier. That you get also, we've seen in several results that you don't get it porosity. You have way higher strength in that weld seam, and therefore you can, for example, reduce wall thicknesses left and right to reduce even the weight.
So it's ready for aerospace as well.
Could be, however, the specifications there are quite lengthy and could be interesting. I think that's not for everyone.
No, but if we look 10 years ahead, it could be next generation.
Absolutely, and I think also for aerospace, they don't care too much about tooling cost.
Yeah. Do you think it can be transferred to other alloy systems? You said magnesium is theoretically possible, but it will start burning if you do that near.
I think there is a bit of a difference that, for example, zinc also is cast well in a high-pressure die casting machine. However, zinc has such a small solidification interval that it really doesn't work there well. And then there are not many processes else, not many materials that we use on these high-efficiency machines. So I think we're quite limited to high-pressure die casting and aluminium as a material system. But I think that's big enough.
Yeah, and in other casting method, you have your inlet, you have your gating. Some also has an after filler that you have to cut off and remelt. How is the efficiency of the material usage in Rheo Casting?
That is, again, super part dependent. So we have parts, for example, let me start over. What we have in Rheo Casting is that we need a very thick gate to allow us to have that low metal speeds. So that is also, it's adding some weight. What we're not going to do or don't need to do is spread it out along the whole casting. So usually when we compare it to high pressure die casting as a reference, we save material there, we save a lot of projected area, which is then crucial to calculate the machine size. And then we have less overflow systems. However, the ones we have are usually bigger. But then we have less material that is recycled. However, it's usually no problem in a foundry as it's sorted by material and then you can just remelt it with the next batch.
Yeah.
So it's no material loss.
Yeah, it goes circular perfectly.
Exactly. It doesn't even leave the shop floor. It directly goes into the melting furnace and you start all over.
And when you have less inclusions, it might also leave you with a better efficiency.
That's usually what we're seeing, that less defects, we get a better outcome. And then that's what you want to have, that you have a process, you set it up once, it runs well, and then you can focus on the things that need build up, that need starting help. And because the ones that are running serious production have to run, you have to make money with that to offset the costs from developing the next applications.
And we're coming to an end, but I'd like to dig a little deeper into the Gigacasting as well, because what will happen there? Now Tesla took a big step ahead as a front runner. But will everybody else follow? And then what will be the next giant step for mankind in the Gigacasting world?
Yeah, so when we look a bit at the history, we've seen, especially looking in old books, we see that high-pressure die casting is quoted as brittle alloys, small parts, porosity, not heatable, not weldable. And it was true until the 90s. Then Audi started with their space frame, with the first aluminum high-pressure die castings that were ductile, were heat treatable. And that was the way they got a little bit bigger in the next iteration, but that was the way how it went. And then Elon Musk came along and said, okay, we are welding all these parts together. This is a casting, this is a casting, this is a casting. Why don't we just cast it at once? Everybody laughed at me and said, that is not possible. We tried that. He didn't listen. He did it himself. And now we have the Gigacasting as a standard for large structural castings, and everybody's running behind. And that sort of especially went well in China. So I would guess 80% of all new electric vehicles are made with a Gigacasting.
The frame of it.
Exactly. So you have a rear Gigacasting, your front Gigacasting, and oftentimes you have a frame for the battery cast as well, and then you just bolt the bottom and the top on.
Yeah.
So there's several concepts. And for the EV startup, it makes totally sense, because if you would have, so a Gigacasting replaces around 70 to 90 parts that have to be individually sourced, welded, riveted, glued together. That is a real challenge to build up such a supply chain. But if you have one casting, you have one supplier, you do it in-house, you can change very quickly, because negotiating with a supply chain is a 2-year process. Changing out an insert in a tool, that takes you, I don't know, 8 to 12 weeks, and you're ready to go. So for them, it's the perfect way, and that continues. So we see now that there's a bit of a stop in installation of new machines, but you see the machines that are out there in China, which is way more than 100 Gigacasting machines in the range of 6,000 to 16,000 ton. They are in operation. They're producing parts that go into cars. So China will go that way. In Europe, we're a bit hesitant. So like usual, there's usually the waiting game. Let's see. We've seen, for example, with Handmann as a first German foundry that invested as a foundry, not as an OEM in a Gigacasting machine. So the demand is there. Volvo is doing it in Gothenburg. So I think it will grow, and then it will depend which platform it will go to. For example, I talked to someone from Ford, and they said, okay, when we consider Gigacasting for the F-150, they're producing around 2,000 of these vehicles per day. The cost saving they get from a 6-week stop and then implementing a foundry, they will never run off, because it's about in the billions they have in lost sales just because they want to implement a foundry to add a gigacasting. So for that volume, it doesn't make sense. But if you have that medium volume, that is a great thing. Or if you're starting out with certain volumes.
Yeah, but the limiting factor is that the pressure you can create in the die casting system, or is it the tool that you cannot produce tools bigger than that, or is it the process making the liquid flow into such a big system? Where is the limit?
So I think that really depends what you define as success. So we're already seeing it that the larger you go, the further the metal has to travel, the more precautions you have to take. So for example, when you have a large machine and you want to fill after 3 meters of flow length, then you suddenly need to increase all your wall thicknesses to get the metal there. So you're producing a heavier part. You need more material. And the larger you go, the more material you need to get the filling to the end. Then people come, yeah, but then we can have multiple machines, but then you have that mixing zone where you don't know how the properties will be, how they mix.
Yeah.
Especially, we've seen it TIG molding machines with 2 short ends. Terrible idea for semi-solid. But hey, people should try what they think should work. And and again, usually it depends. I would say the optimal solution for lightweight vehicles is somewhere in the range of 4,500 to 6,000 ton machine size. Somewhere in that range, you can produce the lightest parts in the lightest vehicles. But you're having less integration than when you have a 16,000 ton machine, but it's heavier. So it's always that game of back and forth.
Yeah. And what is the weight of the biggest part you have seen?
Must be just shy of 70 kilos.
That's also pretty big in one injection system.
In one injection system, and especially if you're standing for it, you can see these parts. It's the whole rear of a vehicle and not a small one. So the area, and then you're standing there, it's radiating heat. So that's impressive.
Yeah, I could imagine. Fabian, this was a great introduction. I learned a lot, but if I would like to learn more and dig really deep, do you have some recommendations where I should go?
Absolutely. We talked at the beginning. Listen to the Gold Casting podcast. We talk about these things way more often than you do on your podcast.
Yeah.
Also, you can sign up for the Casting Insights newsletter where I'm talking a bit about these interfaces between high-pressure die casting, Rheo casting, market development. And if you want to dig down really deep into Rheo casting, I have a course called the Rheo Casting Masterclass, where I really teach the principles on how that semi-solid thing works.
Perfect. And are there conferences or organizations that cover this?
Just as we're recording, there's a conference in Morocco called the S2P conference, which is about semi-solid. But for me, the next big conference will be the China Die Casting in Shanghai. And I'll be also talking about on stage about semi-solid.
Fantastic. Thank you very much. I really enjoyed our conversation, and I hope the audience will reach out to you and bring you in to help them do the Rheo casting in their facility.
Yeah, thank you, Peter, for the invitation. It was really fun to talk about these things. And again, thank you for the invitation.
Yeah, thank you.